Alright, this video is going to investigate how we simplify radicals that look like this, where you see that we've got variable expressions underneath the radical raised to different exponents, and we need to attack those. How do we go about doing that? We've seen a little bit of this. I've done a couple examples through um, kind of the first iteration of simplifying radicals when we just had numbers underneath. We did a couple with variables, but we didn't spend a whole lot of time on it, so I want to go back and do that. Some key concepts in doing this. This is when multiplying like bases, we always add exponents. Okay, this is the laws of exponent concept that we're going to get at here. Okay, so if I have a raised to the mth power times a raised to the nth, which a specific example of that would be this down here, where m is, so that would be the m that they're talking about, and that would be the n they're talking about. When we have a to the m times a to the n, we can rewrite that as a to the m plus n. We add exponents. You've done this a lot when I take x times x, and I get x squared. That's because that's a 1 and that's a 1, and when I add them together, I get that too. Because remember what we're talking about with exponents. Exponents is repetitive multiplication. And that power should tell me how many times am I repeating the multiplication of that thing. Over here, you see that we're repeating it twice, so that's why that's a power of 2. So, specific example says, well, x to the third times x to the fourth. Well, x to the third, that's repetitive multiplication of x 3 times. So that's what that is. X to the fourth is multiplication, repetitive multiplication of x 4 times. Okay, so if I do that, and remember that there's a symbol right here between these two of multiplication. That's multiplication right there, meaning that this is multiplication right there. Now I've got repetitive multiplication of 7, or x being multiplied by itself 7 times. So I can rewrite that as x to the 7th. But that is also, how do I get that 7? That 7 was the sum of that 3 and 4. And what we're going to do then is say, okay, well, if I had like x to the 8th, there's a lot of different ways I could write x to the 8th. I could rewrite that as x to the 4th times x to the 4th. I could write it as x to the 5th times x to the 3rd. I could rewrite it as x to the 6th times x to the 2nd. Okay, now I could go like 3 and 5 and 2 and 6, but that's because of multiplication being commutative, they're the same. So if I went x to the 5th times, x to the 3rd times x to the 5th, that would be the same thing as that. And the last one I could write it as is x to the 7th times x to the 1st. And this is actually the one that we're going to be really interested in, is when we can get that to be a 1. Okay, or one of these bases to be a 1. But that's one of the key concepts that we're going to use when we work with the simplifying of algebraic expressions underneath our radical. So we'll use this property. We will use, there shouldn't be a D there, this property in reverse to help with simplifying radicals with algebraic expressions. So we're going to start with that. And we're going to get down to something like this, or one of these other configurations. It says, in addition, we'll use the fact that the power of 2 and the square root are inverses of one another. That is, they undo each other. It says this can be extended to a power of 3 and a cube root, power of 4 and 4th root, and so forth. But this is the rule that we've talked about in the past. If I have, maybe one of the simplest ones we know of is like the square root of 9. Well, square root of 9 is the same thing. 9 is 3 squared. Why is the square root of 9 equal to 3? It's because 9 can be written as 3 squared, and then the square root and the power of 2 cancel each other out, and just leaves me with 3. In this case here, the n would be 3. 3 squared underneath the root will just give me 3. Okay, so the square root of something squared is just that something. So we use that approach, that concept as well here. But we got a basic procedure, and this is several steps and a couple different sub-steps, but this, you should be able to go back to this if you get stuck on any of these. First thing we're going to do, or at least I'm going to teach you to do, is to break apart the numerical and algebraic parts. So let's just kind of come over here to the side and do one of these. Let's say that we have radical, let's make sure I don't do one that we, okay. So radical 8, let's go x to the 7th, y to the 6th, something like that. Okay, it says break apart the numerical and algebraic parts. What I mean by that here in step 1 is to do this. Take the radical 8 and write it in its own radical, and then take the algebraic parts and rewrite them. Okay. 1a says then simplify the numerical part as previously done, as we've worked on for now almost going on 3 weeks. Okay, so what we're doing with the variable components is actually the reason for the procedures we've learned for simplifying strictly numerical radicands. So what we're going to be doing here with these variables is exactly what we've been doing with this radical 8, looking for perfect squares that divide 8. Okay, but in this process, you're going to go 8, it goes down to 2 and 2, sorry, 2 and 4, and then the 4 goes down to 2 and 2. So there's a group of 2's that can come out front, and then I got a radical 2. Okay, but really what that was meaning, and this is where we can get the kind of the comparison to what we're going to do with our variables, that really means when I had this 2 times 2 times 2, it's 2 to the 3rd, but I'd rather rewrite that as 2 squared times 2. And now I can break it up that way. Power of 2 and the root of 2 cancel out, and it leaves me something like that. Okay, and if you can do that, that's great, okay, because that's going to help you a lot with these variables. If you can't do that yet, the hope is that working with these variables will get you there. We'll get you to be able to do what I just did here. We got 2 radical 2. Okay, that was just the 8. Okay. Now it says rewrite all odd degree variables as a product of like bases, with one of those bases being raised to the power of 1. Okay, so this x to the 7th, that's the one we're talking about here, because it's the it says rewrite all odd degree variables. Okay, so I'm going to take x to the 7th and rewrite that as x to the 6th times x to the 1st. Okay, that's all I want to do there. Okay, and that's exactly what I did here with this 2 to the 3rd. I rewrote it as 2 squared times 2 to the 1st when I was dealing with the 8. Okay, it says now that you have something like x to the 6th, that can be written several ways. Okay, so x to the 6th, you can do this multiple ways. We can rewrite that, and remember, it's all underneath the radical. So I can rewrite that as x squared times x squared times x squared. And we've talked about how that can be rewritten as x squared under its own radical, x squared under its own radical, x squared under its own radical. And then if that's the case, then that and that will cancel, leaving me just x. That and that cancel, leaving me just x. That and that cancel, leaving me just x. I get x times x times x, which yields x cubed. Okay, which if you look at x cubed compared to x to the 6th, the 3 is half the 6, and that will always be the case. So that's one way of writing it. Another way of writing that x to the 6th is to say that x to the sixth is the same thing as x to the third squared. Okay, you can always take an even power and write it as an odd power squared. Okay, doesn't even have to be an odd power; it could be an even power squared. But you can always write it as a power squared. So now if I square root this, I'd be square rooting that, and now we find out that this root and that power of 2 cancel, and all you're left with is x to the third again. Regardless how you view it, square root of x to the sixth becomes x to the third. Okay, that's where we get down here to this argument here. It says every time you get an even power in the radicand, you take half the power, and that comes out in front of the radical. And that always is the case. Okay. So as we're working through this problem, I broke down x to the seventh as x to the sixth times x to the first. Y to the sixth is going to stay y to the sixth. So what we're going to do is, once we've done this, we're going to take this here. And the reason we can do this is what we just said here in step 3. But I'm going to take that, take half of the 6, and it comes out front. So I've already got a 2 out in front because of the number part. This turns into x cubed, it comes out in front. Okay. This y to the 6th is even as well, so I'll take half that 6, and that can come out in front. Now, when we do that, when something gets cut in half and brought out front, it's gone underneath the radical. There's nothing there left underneath that radical with that x to the 6th and y to the 6th. But this x to the first, that's an odd power. Okay? We can't break that down. It's just going to be x. Okay? It's much like this 2 right there with the 8. When we're breaking down the 8, it didn't have a partner. This x doesn't have a partner. Okay? And then I've also still got this radical 2 that came from the numerical part. So that's going to be multiplied back together underneath the radical. And the best way we like to write that then is 2x cubed, y cubed, times the root of 2x. Okay? So, it says you'll do this for every variable present, like I did with x and y. Last step says use technology to make sure that you have an acceptable version. Technology isn't always going to tell me that I've got the most simplest version, but it will tell me that I've got a acceptable version. So if I type in square root of 8x to the 7th y to the 6th. Okay, obviously it doesn't right now give me any quantity here, any numerical representation, because I don't have x and y defined. But I'm going to jump down to the next line. I'm going to type in what I think my simplified version should look like. 2x to the third, y to the third, times the square root of 2x. Okay. Now, I'm going to get a lot of students to say, well, I don't know where you come from, but this looks a lot simpler than that. And I would agree with that. Okay. But this is considered the simplest version because when identifying the simplest version, we're only comparing the radicands. So that radicand is much simpler than that radicand. Okay, so that's why this is the simplest version. Not just going off of looks, but going off of what it does for us mathematically. So now here, all I got to do is define my terms. So I'm going to let x be some number. Let it be 2. My suggestion here is always let your variables be positive, because if you let them be negative, there could be a situation where you get a negative product underneath here, and you can't take square root of negative, and your computer or your technology is going to kind of balk at that. I also suggest not letting your variables take on the same number. So if x is 2, I'm going to let y be something other than 2. Okay, I try to avoid 0, and I try to avoid 1 and negative numbers. But everything else is kind of fair game. But I'm going to plug in 3 here, and you see that when I do that, these two things equate to the same number. So that suggests to me that these two versions over here are the same. Okay. Now it could just be happenstance that I got, maybe 2 and 3 are two numbers out of all numbers exist that I randomly chose, and that's the one time that they're equal. Okay. So I'm going to try maybe putting 21 in there and 3. And you see I get the same number there. Maybe I put 21 and pi in, and you see that I get the same answer. So that's pretty rare that I'd be getting the same answers with numbers like that. Okay, so what that tells me is that these two representations are identical. That is then indeed my simplified version. So as we work through these, I'm not going to every single time, probably won't do it very often at all in this video. Come back to the technology to make sure that we've got them simplified. But if you get stuck on homework, stuck on a test or quiz, get confused, did I do what I'm supposed to do, that type of thing, grab this. Grab your calculator and kind of sift those rules and properties out. All right, so some examples here. I'm going to take the approach that we can simplify radical 12. Okay, so going through the steps above, I said break apart your numerical part and your algebraic part. Okay, so radical 12, and that goes to 4 and 3. 4 is a perfect square, so that can come out. And 3 is going to stay underneath. Okay. One way of doing this that you might kind of prefer, and I'm actually going to come down here at the bottom and do it. When I write my answer for the most part is going to have a radical. So maybe that's what you do. You put your radical in and say, okay, now there's going to be values or expressions that come out front, and there's going to be values or expressions that stay underneath. And I just start filling those things in as I go. So I'm done with the 12. Okay. Now we said in the algebraic part, every odd base needs to be rewritten as an even base, or a base raised to an even power times a base raised to the first power. And basically what you're going to do, no matter what the number is, if it's 5, you're going to have one less than that. It's going to be 4. It's going to take you to the even number below it. If it's 13, you're going to go to 12. If it's 71, you'll go down to 70. Okay? And then the other one will be obviously a to the first, because those two multiplied together give me a to the fifth. B to the seventh is going to go down to b to the sixth times b to the first. And now we said go find the ones that are even. So a to the fourth, the square root of a to the fourth, because that's even, we take half of that 4, and it comes out front. And then you're done with it. Now this a to the first doesn't have any partners. Okay? Then we're going to go b to the sixth. B to the sixth, that's another even one, so I'll take half that. It becomes b to the third. And then this b to the first. And we're done. Let's go over here to do the same thing with this one. So separate them. Got radical 18. And then x to the 8th, b to the 10th. So 18, that's 9 and 2. 9's a perfect square, so that's going to come out as a 3. And then 2 stays underneath the radical. Now if I attack the variable part, okay, that was even, so I don't need to do anything with that. I'm going to take half of it and bring that half out front. Same thing with b to the 10th. 10 is even, so take half of 10, and you get 5. So 3x to the 4th, b to the 5th, root 2. Over here, so we get root 24. Some people like to do this. It doesn't matter. You can do it this way. Just take every single thing and put it underneath every single term. So 24 m x squared r to the ninth. Some people like doing that. It's fine. Laws of exponents say that's okay. So when I'm done, we'll have something out front of the radical, something underneath the radical. Let's look at this 24. 2 and 12. 12 goes down to 4 and 3. Perfect square. So that comes out as 2. 2 and 3 don't have any partners. So they multiply together and get 6 and then go underneath. Now this m to the first, okay, that is odd, but I'll never, if it's to the first power, it's staying underneath the radical. So you're never going to write, like, since it's odd, you'll never write it as like m to the 0, m to the first. Doesn't make sense to do it that way. X squared, that power of 2 is even, so those are going to cancel, leaving me x to come out in front. This r to the ninth now, well, we're going to take r to the ninth and rewrite it this way. R to the eighth times r to the first. So now you got an even power there, so r to the fourth can come out, half of that 8, and then this r to the first stays underneath. This one here has already got some stuff out in front, and there's really no need to let that worry you. You're going to now, just when you have an answer when you're done, there's already a 3x out there. So I'm going to break this apart. We'll have the 3x already out there. We've got radical 28 and radical x to the fifth, y to the fifth. So dealing with the 28, 2 and 14, 2 and 7. So a 2 can come out, and a 7 will stay underneath. So I'm done with the 28. That 3x is already out there. X to the fifth. Remember, we write that as x to the fourth times x to the first. And then y to the fifth will be y to the fourth times y to the first. So take half of that one. This gives me x squared. X to the first stays underneath. Take half of that one because it's even, so y squared. And then this y to the first stays underneath. Just got to pay attention to the things that are outside. If you got like bases out here, you need to multiply them. So 3 and a 2, so give me 6. Here's x to the first and x squared. So that's going to add those exponents, so it's going to be x to the third. And I got y squared out there. And then 7xy underneath. Similar thing here. We got some options here. You can take these individually and work with them individually. So, and then just at the end multiply. So, let's do it that way first. Let's look at this one here and rewrite this as root 40 times, and so x cubed will be x squared times x to the first, and then y squared. 40 goes to 4 and 10, 10 goes to 2 and 5, perfect square. So in my answer, a 2 can come out in front, and a 10 is going to stay underneath. Now with the x cubed, that turned into that, so half of that one can come out in front, and that one stays underneath. And this y squared, the y can come out. So half of the power 2 comes out front. So that gives me the square root of 40x cubed y squared. Okay, but we're going to multiply that by, we'll do this in blue, that thing right there. So that one's going to separate as root 8 times root x, y cubed, I'm going to write as y squared times y to the first. We've already done radical 8 previously, so I'm just going to say that's 2 radical 2. Okay, now working through, this x stays underneath. Y squared, so it's even, so y can come out. And then this y is going to stay underneath. Okay, so when that happens, now we've got all of this, we've got multiplication now of these two things. We got the red one multiplied by the blue one. So now, multiplication rules kick in for radicals. We're going to multiply the numbers on the outside. So 2 times 2 gives me 4. X, and now y times y gives us y squared. Underneath, 10 times 2 gives us 20. We have x times x gives us x squared, and then we got our y. And the only thing about this that stinks doing it this route is that 20 and that x squared are no longer simplified. So now we got to do that. Okay, so 20 breaks down to 4 and 5, 4 being perfect square. So I've already got this 4xy squared out front. This 2 from the 20 can come out. 5 will stay underneath. This x squared, okay, because it's even, an x can come out for that, and this y stays alone. So now, multiplying like terms, we've got x times x on the outside here. So it's going to be 4x squared, y squared, times the 2 that's out here. So that 4 and that 2 are actually going to make this coefficient an 8. And they got 5y underneath. And that can be kind of a tedious task. We've done a lot of work there, so it makes sense, I think, to go see if what we've done here matches up. So I'll take square root of 40x to the third times y squared, and we'll multiply that by square root of 8 times x times y cubed. See if that's the same thing as 8x squared y squared times the square root of 5y. So once we type those in, we are then going to define our variables. So x, like I said, I usually just let x be 2, y be 3, and go from there eventually. But we see then that those two things are identical, so those work out to be the same. And that's an approach to think about if you like it that way. What I don't like about that is, especially the first kind of go around with this stuff as you're learning this maybe for the first time. This should not be the first time we've learned this, though. This is an Algebra 1 standard. The issue arises that people think, well, I simplified this right here, I simplified this right here, and I multiply them together, I've done all my simplification. But because multiplication occurs, some products materialize that are not simplified, and we have to remember that we have to do that one more time. This approach is going to be maybe a little bit better in regards to that you don't necessarily have to simplify multiple times, but this is going to create larger coefficients and constants, I guess, underneath the radical. So what we can do here is actually remember, if we're multiplying radicals, we multiply the numbers on the outside. So 1 times 1 gives me 1. And we multiply the things on the inside. Well, 40 times 8, okay, 40 times 8 is 320. Okay. Then I got x cubed times x. x cubed times those are like bases, so you add the exponents, so you x to the fourth. And then y squared times y to the third, add those exponents, and you get y to the fifth. So that might be easier because now I could take radical 320 and I've got x to the fourth, y to the fifth. The payoff, I guess the payoff here is that we want to simplify multiple times, but the cost is, instead of looking at like simplifying 40 and 20 as we did over here, now we're simplifying 320. But if I take 320 and break it down, I see a 32 and a 10, 8 and a 4, 4 and a 2, 2 and a 5. I'm going to stop here. I've got, there's a perfect square that can come out in front as a 2. There's a perfect square that can come out in front as a 2. Here's another group of 2's that can come out in front. And then that 5 does not have a partner. So 2 times 2 times 2 is 8 times radical 5. And back over here, we had an 8 out front. We had a 5 underneath. So on the right track. Now coming to the variable part, well, that's even, so I can rewrite that half of that out front, so x squared. And y to the fifth, remember y to the fifth can be rewritten as y to the fourth times y to the first. Now that's an even power, so take half of it and it comes out in front. And y to the first is odd, it's first power, so it stays underneath. And you see we get 8x squared y squared, exactly what we had there, root 5y, exactly what we had there. I think this route's faster, but like I said, the cost of it is you're going to be simplifying generally larger radicands that are numerical like that. These next two are similar, just incorporating now one more of our radical rules, that in this case was division. And all this is saying then is if I want to do this, we can separate them. So the numerator becomes 3x cubed y squared. The denominator, root 64a to the sixth. So basically you're going to treat this as two problems. You're going to work with the top, root 3, and then x cubed can be rewritten as x squared times x to the first. Y squared stays as y squared. On the bottom, I'll have root 64, and then a to the sixth. So now working, probably not give myself enough room with these. Working along the top then, obviously the root 3 doesn't simplify any. X squared comes out as an x. This y squared comes out as a y. And then underneath the radical, I have x. On the bottom, 64 is a perfect square, so 8 comes out. And this is even, so a to the third. Nothing is left over. That went away as 8, that went away as a to the third, so there's no radical. If you want to put radical 1 there, there's nothing wrong with that. I think Math Excel would probably count it wrong just because it's just not something that they're looking for. But it is not wrong, but usually we write that way. The one thing to pay attention to when you do this is to make sure that these things are fully simplified out front, that there's no common factors there, which I think we might see here in this next one. So this one here, we got our 64, and we'll have x to the fourth, x to the fourth, m to the ninth equals, on the bottom here we'll have root 36, and then x to the sixth, m to the sixth. Alright, so the top square root of 64 is 8. This x to the 4th, take half of it and it becomes x squared. M to the 9th, remember that's m to the 8th times m to the 1st. So the m to the 8th can come out as m to the 4th. And then m to the 1st stays underneath. The bottom, 36, is square root of that is just 6. X to the 6th can come out as x to the 3rd. And m to the 6th can come out as m to the 3rd. And now, I'm going to rewrite this down here. We have 8x squared, which let me just write it this way just so we can make a comparison of what we're going to be doing here. X squared is x times x. M to the 4th is m times m times m times m times then root m. So that's the numerator expanded, not using powers. And the bottom would be 6x times x times x times m times m times m. What I want you to realize is that both these have a power of, or not a power, but a factor of 2 in them. So let's divide 8 by 2, and that will give you a 4. And let's divide 6 by 2, and that will give you a 3, so that's reduced. Now, this right here, x over x, something divided by itself is just 1. So those cancel. Here's another situation where we have x divided by x. Those cancel. Here, we have an m divided by an m. Those cancel. Another m divided by an m. Those cancel. M divided by m. Those cancel. So up top, you're left with 4m root m. On the bottom, you're left with 3x. Okay? Some of you might prefer or recognize that, well, I could have done the same thing here. So x squared and x to the 3rd, if they're canceling, there's more x's on the bottom, so all of these up top are going to cancel away, leaving me with just 1 on the bottom. And when I look at the m's, they're going to cancel as well, but because there's more m's on top than in my answer, I'm going to have m's in my numerator and not in my denominator. Hopefully that's of some use to us. There's an assignment in Math Excel for you. Let me know if you have any questions.